In a previous lecture, we talked about the variance of the OLS estimators B1 and B2, and we realized that those are unknown to us because they depend on this unknown parameter sigma square, where sigma square was the common variance of the error terms. The basic idea in econometrics, whenever we have an unknown parameter like sigma square, is to go ahead and try to find an estimator of it. And that's precisely what this lecture is about. We will try to figure out an estimator of sigma square. The estimator will be denoted by S square. So let's just start with a simple setup where we have a linear regression model with random sampling. At this point, no need to introduce any further assumptions of exogeneity or homoscedasticity. We can define S square just based on a random sample. This is how S square is defined. It's defined as RSS, remember, that was the sum of squares of the residuals divided by n minus 2. So 1 over n minus 2 times the sum of the squared OLS residuals. Actually, it doesn't even have to be the OLS residuals. We can define S square using any residuals. So this is what you can say about S square. If the Gauss-Markov assumptions are satisfied, that is, if the explanatory variable is exogenous and we have homoscedastic errors, then this S square guy will actually be an unbiased estimator of sigma square. Without Gauss-Markov, this will not be true. If you have heteroscedastic residuals, for example, sigma square doesn't even exist, so there is no issue of whether S square is unbiased of it or not. You can also show that S square is a consistent estimator. Again, remember what that means? It means that as n goes to infinity, S square will become equal to sigma square. While the first bullet point tells us that the expected value of S square is sigma square. So let's have a look at this in the regression analysis. And let's add sigma square because I only have sigma here. So let's add sigma square as well. And that's then just simply equal to this guy squared. That's unknown. We're going to paint it red. Just make sure that we realize that we don't know this value. So how would we estimate this guy in this Gauss-Markov world? Here in this simulation study, the Gauss-Markov assumption is satisfied. The error terms all have expected value 0 and they have a constant variance. Well, we can use the fact that if you have a random sample, then the sample variance will be an estimator of the true variance. The error terms, they have a true variance of 0.25, so I can use the sample variance of these guys as an estimator of sigma square. Can check that this makes sense. So if I just write var dot s, the sample variance of all the error terms, like that. And if you look at this and you F9, you see that this is a very good estimator of this one in cell B7. If I F9, you can see that this number does seem to be unbiased. It's sometimes above 25 and it's sometimes below 25. All right, so now the big problem is that this one is red as well. Because it's calculated from the error terms and we don't know the error terms. So that was kind of a dead end. Fortunately, we have an alternative. we talked about the fact that the OLS residuals, the E's, they tend to be close to the error terms, simply because the B's tend to be close to the betas. As you can see, they're definitely not terribly close to the error terms, but close enough for this idea to work. So instead of looking at the sample variance of the error terms, I can look at the sample variance of the residuals. Let's summarize this discussion. So 1 over n minus 1 epsilon I minus the average of the error terms, I go from 1 to n. That's the sample variance of the error term. That's a good estimator of sigma square, which is the actual variance of the error term. The error terms are not observed, but we do have this fact that they tend to be close to the residuals, at least if my OLS estimates B are close to beta. So the idea is to replace the residuals with the error terms in the estimate of sigma square. So if I look at the sample variance of the error term, let's just write sample variance of, if we look at the sample variance of the residuals, write it like that, it would be 1 over n minus 1 summation ei minus e bar squared instead. And of course I forgot the square here, sorry about that. If the ei's are close to the epsilon i's, then the sample variance of the e will be close to the sample variance of the epsilon. Well, we know that if we use OLS, then this is 0. So this is 1 over n minus 1 summation ei squared. So we could use this as our estimator of sigma square. It turns out that we do something which is just slightly different. We replace n minus 1 with n minus 2. So 1 over n minus 2 summation ei squared is used as an estimator of sigma square. I'll come back to this n minus 1, n minus 2 issue in a second. So here, as my estimator of sigma square, I'm going to use RSS, which is the sum of squares of all my residuals, I2 colon I21, and I'm going to divide it by not 19, but actually 18. So this guy is going to be the estimator of this guy. And as we discussed in the lecture, it's actually going to be an unbiased estimator. And the way you should really think about that is that if I F9 this guy, if I redo the experiment over and over, pay attention to this one in I22 and compare that to 0.25, then this number is going to be, this random variable is going to be unbiased. It's going to be above 25 and below 25, but on average it will be 0.25 if I keep on going. And it will be consistent in the sense that if you increase the sample size and let the sample size go to infinity, this number will become equal to 0.25. So now I can also explain why we did this, why we changed n minus 1 to n minus 2. Well, it turns out that it's just a statistical technical detail. It turns out that this guy will not be unbiased, while this one will be unbiased. So changing n minus 1 to n minus 2 is sort of a bias correction, which we have to do because we are using residuals instead of error terms. The full mathematical details behind that is a little bit more tricky, and that's not going to be covered in this lecture. So to review the whole thing again, if I have a linear regression model with random sampling and I assume the Gauss-Markov assumptions. If I assume the Gauss-Markov assumptions, I'm introducing a third unknown parameter, namely sigma square. We need to estimate this parameter sigma square in order to estimate the variance of B. And the estimator that we end up using in this case is the estimator called S square. S square is pretty easy to calculate. You just take RSS and divide by n minus 2, dividing by n minus 2 just to make it unbiased. We base the estimator of sigma square on the residuals instead of what we would actually like to base it on, namely the error terms, simply because the error terms are unknown to us while the residuals are known to us. So then you can show, and we don't do that in this lecture, that it's unbiased and it's consistent. A final point is that if you take the square root of this number, 0.18929 in this example, which you can always do because it's a sum of squares, then it's common to call that thing, that was just the consistency, it's common to call that thing the standard error of the regression. So S, the square root of S square, the standard error of the regression. And just like S square being a consistent estimator of sigma square, S will be a consistent estimator of sigma. Another way to say that, the standard error of the regression is a consistent estimator of the standard deviation of the error terms. Before we finish this lecture, let's see how we can calculate S and S square for actual real data, because this method here is not really appropriate. It's just way too long because we have to go through, find residuals and all that stuff. In Excel, you can actually find S quite easily. What you have to do is, instead of marking up two cells, what we do when we just want to estimate B1 and B2, you mark up 2 and then you mark up 5 rows like this. You type the same thing. That is, you type equal linest, you do your y variables like that, you do your x variables like that, you tell Excel that you indeed want to include a constant, and here's the thing. And now we want the statistics. So let's do true or 1 here. Shift Control Enter, and you can see you get a bunch of additional data here in addition to B1 and B2. You can see precisely what these numbers are representing. If you click the symbol, click the help on this function, then we can just go down to, let's see here. This tells you that the first row has the OLS estimates, the second row has something called standard errors. Here in the third row, first element, you have R squared. This is actually R squared, called R2. And the one we're looking for is this one, sum of squares of residuals. So that's this one, 6.18 is the sum of squares of the residuals. So if I just close this guy, cancel. In this experiment we have R squared, 0.966625, and I can calculate here the S square. It's just simply this guy divided by n minus 2, which is 18, and that should come out to be 0.3436 as well. Well, now it redoes the simulation, but you can see that these numbers are indeed the same. So that's S square. In eViews, you can just bring in your data. This is some data on wage and years of schooling. Run your regression, quick, estimate equation. Let's say we want to explain wage on a constant and years of school, like that. Then you will have the S value right here, the standard error of regression, 3.14 something. If you want to, you can double check this because here you have RSS, the sum of squares of the residuals. So if you take this number, divide by n minus 2, where n is right there, that will give you S squared. Take the square root of that and you see that you come up with exactly this number right there. In Gretel, same data set, you can just go to model, ordinary least squares, make wage your y variable and make school your x variable, do OK, and Gretel puts it right here. That's the standard error of the regression. And we have our estimate of the standard deviation.